NASA's twin Voyager probes, launched in 1977, captivated the world with historic journeys to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their exploration into interstellar space, even 45 years later. Researchers, some newer than the spacecraft themselves, are still utilizing Voyager data to unravel mysteries both within and beyond our solar system. In many ways, the twin Voyager spacecraft have become time capsules of their era, with around 3 million times less memory than today's smartphones and a transmission speed 38,000 times slower than a 5G connection. Each probe contains an 8-track tape recorder for data storage. Despite these limitations, the Voyagers remain at the forefront of space exploration. What are they doing now, and what will they encounter next? Let's find out. Two of the most remarkable spacecraft ever launched would never have taken flight had the stars not aligned quite literally. The alignment of the 4 largest planets in our solar system allowed a spacecraft to gain speed from each planet's gravitational pull, as if tugged by an invisible rope. However, this alignment only happens once every 176 years. This meant NASA needed to launch a spacecraft by the mid-1970s to take advantage of this rare planetary lineup. As a result, NASA created 2 spacecraft to seize this once-in-a-lifetime opportunity. Within 15 days of each other, Voyager 1 and Voyager 2, identical in every way, were launched in the summer of 1977. They have since operated for nearly 45 years, sending data back to Earth every day from the farthest reaches of our solar system. These spacecraft have traveled farther and lasted longer than any other in history. According to current understanding, they have entered interstellar space, becoming the first human-made objects to do so, a distinction they will hold for decades. Not bad for missions initially intended to last only a few years. Early Voyager observations stunned researchers, revealing active volcanoes and frozen ice fields on moons astronomers had assumed were as inactive and cratered as our own. Voyager 2 became the first spacecraft to pass by Uranus in 1986, and 3 years later it flew by Neptune, becoming the only spacecraft to do so. Today, both Voyagers continue to surprise physicists with new discoveries about the unexplored regions of space, more than 12 billion miles from Earth. However, their amazing voyage is coming to an end. In the past 3 years, NASA has turned off heaters and other non-essential components to stretch the spacecraft's energy reserves, hoping they will last until around 2030. For the scientists involved, many of whom have been with the mission from the start, it is a bittersweet moment. Voyager 1 reached Jupiter 546 days after its launch in March 1979, and Voyager 2 followed a few months later. The spacecraft, equipped with cameras that used red, green, and blue filters to create full-color images, were built as stable platforms. The rotation speed is 15 times slower than the crawl of a clock's hour hand, minimizing visual blur as they travel across space. Even 3 to 4 months away from Jupiter, they began transmitting the first images, delighting standing room-only crowds at NASA's Jet Propulsion Laboratory JPL. One of the most unexpected discoveries was that Io, one of Jupiter's moons, had active volcanoes. Before the Voyager missions, it was assumed that moons in the solar system would all be drab and cratered like our own moon. However, Voyager revealed an incredible diversity of landscapes near Jupiter and Saturn. As the spacecraft approached Jupiter, one of their detection systems recorded unusual signals, leading to the discovery of Io's volcanic activity. The small moon, slightly larger than Earth's moon, is now known to be the solar system's most volcanically active body. Its volcanoes spew material that gives Io its unique colors and create towering plumes that can rise 30 times higher than Mount Everest. Voyager captured over 33,000 images of Jupiter and its moons, each revealing something new. As the spacecraft left the Jupiter system, they received a gravity boost of 35,700 mph, enabling them to escape the sun's pull and continue their journey to other stars. At Saturn, the Voyagers parted ways. Voyager 1 passed by Titan, Saturn's largest moon, and then turned north away from the plane of the planets. Meanwhile, Voyager 2 continued on to Uranus and Neptune. In 1986, Voyager 2 discovered 10 new moons orbiting Uranus, and in 1989, it observed the fastest winds ever recorded on a planet, with speeds up to 1,000 mph on Neptune. It also captured images of Triton, Neptune's largest moon, one of the coldest places in the solar system, with surface temperatures reaching 391 degrees 235 degrees G. As the grand tour ended, NASA intended to turn off the spacecraft's cameras since no more photo opportunities would arise. However, astronomer Carl Sagan pleaded for one last set of images. As a result, on Valentine's Day in 1990, Voyager 1 turned its cameras back toward the inner solar system and snapped 60 final images. The most famous of these is the pale blue dot showing Earth as a tiny speck in the vastness of space, captured from 3.8 billion miles away. This remains the farthest depiction of our planet ever taken. Today, both Voyagers are so far from Earth that radio signals traveling at the speed of light take nearly 22 hours to reach Voyager 1 and over 18 hours to reach Voyager 2. They advance by 3 to 4 light seconds each day, and NASA's Deep Space Network, a global array of tracking facilities, is their only connection to Earth. As they journey farther into space, their signals grow fainter, and communicating with them becomes increasingly difficult. Yet, even these faint signals have reshaped astronomers' expectations for what the Voyagers would discover as they move into the interstellar regions of their journey. It is important to distinguish the solar system's boundary from that of interstellar space. The Oort cloud, a distant collection of comet-like objects bound by the Sun's gravity, may extend halfway to the nearest star, and it will take the Voyagers another 300 years to reach its edge. However, interstellar space is defined as the region where the solar wind, a stream of charged particles emitted by the Sun, ends. The solar wind inflates a bubble, known as the heliosphere, which is eventually halted by interstellar matter, creating a boundary known as the heliopause. There is a border between our solar system and interstellar space, and estimates of its distance before the Voyager missions fluctuated significantly. According to some, these were just assumptions. One early guesstimate placed the heliopause as close as Jupiter. However, Garnett's calculations from 1993 estimated the distance to be around 25 times further, between 116 and 177 astronomical units. 1 astronomical unit AU is the distance between the Earth and the Sun, about 93 million miles. Garnett's projections from 1993 proved accurate when one of the Voyager spacecraft eventually reached the heliopause, though about 20 years had passed. Voyager 1 had detected the anticipated rise in plasma density. Its plasma wave detector inferred an 80-fold increase. But surprisingly, there was no indication of a shift in the ambient magnetic field's direction. Shouldn't such a change have been apparent if the spacecraft had traveled from an area where the magnetic field originated from the Sun to one where it came from other stars? That was an unexpected discovery. In November 2018, Voyager 2 arrived at the interstellar boundary, but it did not detect any changes in the magnetic field either. When the spacecraft reached the heliopause at around 122 astronomical units from Earth, the same distance reached by its twin 6 years earlier, it added yet another puzzle. All theoretical models predicted that the heliosphere should expand and contract over time in line with the Sun's 11-year cycle. However, these findings did not fit any of the existing models. At the time Voyager 2 arrived, the solar wind was at its strongest, meaning the heliopause should have been further out than predicted. Theorists' models of the interaction between the heliosphere and interstellar space are becoming more intricate, now that the Voyagers are providing real field data. According to the general understanding, our Sun left a hot ionized zone and entered a patchy, partially ionized section of the galaxy. The hot zone likely developed as a result of a nearby supernova or several supernovae exploding at the end of their lifetimes, heating the surrounding area and stripping electrons from nearby atoms in the process. One way to conceptualize the boundary enclosing that area is to think of it as a seashore, with water and waves whirling and mixing together. Magnetic fields twist and turn within this turbulent area. The degree of turbulence varies depending on the method of observation, but it is not the smooth magnetic fields that theorists typically prefer to model. As a result of the heliosphere's influence on the interstellar medium, the Voyager data reveal numerous small-scale changes near the heliopause, but negligible field variations at larger scales. It is expected that the spacecraft will eventually move beyond these turbulent zones and come into contact with a purer interstellar magnetic field. Saying goodbye to these innovative spacecraft won't be easy. Seeing things come to an end is difficult. Currently, Voyager 2 has 5 operational instruments and Voyager 1 has 4. Both spacecraft are powered by a system that converts heat from plutonium radioactive decay into electricity. However, NASA has been forced into triage mode as the power output is diminishing by roughly 4 watts per year. Nevertheless, the Voyager's journeys will continue even after they go completely silent. Voyager 1 will pass our closest neighboring star, Proxima Centauri, in 16,700 years, and Voyager 2 will follow 3,600 years later. After that, they will spend millions of years orbiting the galaxy, long after our sun has disintegrated and the heliosphere has vanished, not to mention our pale blue dot. The Voyagers will still be there, largely undamaged. They might even send a final message, but it won't be broadcast over radio waves by humans. The message is stored on 2 golden records, outdated technology, but not the typical plastic variety. These records are made of copper, coated in gold, and housed in aluminum. Encoded in the grooves of these golden records are sounds and images meant to convey a sense of the world the Voyagers came from. There are 90 minutes of music, including Bach's Brandenburg Concerto No. 2 and Chuck Berry's Johnny B. Good. The records also include images of children, dolphins, dancers, sunsets, and sounds of crickets, rain, and a mother kissing her child. Jimmy Carter, who was President of the United States when the Voyagers launched, also left a message. We cast this message into the cosmos. It reads in part: "We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope, determination, and goodwill in a vast and awesome universe." Thanks for watching another episode of Space Discovery. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.